Um, Today at the data science seminar, we're gonna hear from Adam Visokay, who is a PhD student at University of Washington, advised by Professor Tyler McCormick. They're also an affiliate student at the Max Planck Institute for Demographic Research. Adam's research explores how to leverage artificial intelligence and machine learning to study social phenomena typically motivated by questions in public health, economics, and sociology. Adam is particularly interested in improving the interpretability and transparency of language models and how to perform valid statistical inference using predictions. Thank you so much, Adam, and welcome to our seminar today.
Thank you. Thank you so much for having me. Hi, everyone. I'm Adam. I'm a second year in the sociology department here, and I'm excited to share some of my work with you. So first, before I just get started, I want to give a quick plug to eScience, who actually provided the computing credits that I used for all of the research you're about to see. So big thank you to them for making that possible. Thank you, eScience. Okay, so first, here's the research team. I'm one of many collaborators working on these projects. Trinity and myself are both graduate students here. Trinity's in the statistics department. And then we have 2 postdocs, Kentaro and Steven, and then 4 faculty members at the UW, and then Johns Hopkins University, Fred Hutch, and UW. So all sorts of people working on this. Couldn't have done it myself, and very excited to talk about it with you today. So very quickly, here's the roadmap for today. I want to talk about doing inference with predicted data. All right. And so before we get into the details, I want to give kind of an overview of what I mean when I say the word estimation and when I say the word prediction, how they're different, how they're related to one another. Right. I think for me, when I was getting started in this body of work, that distinction was not obvious to me, and I got very confused over and over. So I think I'm going to linger there a little bit, and hopefully it's not too redundant, but I think that's a really important sort of link to make the rest of this make sense. Okay. The next thing I'm going to talk about is actually what is inference on predicted data and why is it a challenge and how do we fix and solve that problem? And then I have 2 sort of empirical examples. One is going to be working with verbal autopsy narratives. These are text data in sort of a public health setting. And then BMI, the body mass index, which you might be familiar with, as a prediction algorithm. This is more in a medical setting. Okay, and then leave some time for questions and answers. So also feel free to please raise your hand and interrupt with questions. I love answering questions, so don't be shy. Okay, so let's talk about estimation versus prediction. What are the differences? Okay, so if you've ever studied like linear regression, right? This first line here, that's sort of like your basic linear regression, right? This is sort of like your slope intercept form. Y equals mx plus b. In this case, this is like a beta coefficient, right? But the idea is we want to kind of explain y, our outcome, as a function of x, our sort of variables of interest. Beta are these like associations, right? So when you run a regression and you get your sort of table of estimates, these are your sort of estimated parameters, right? This is telling you like the marginal effect of a change in y on your outcome of variable or outcome variable of interest y, right? And this is beta hat, right? This is an estimated parameter. Okay, so I talk about estimation. I'm talking about this sort of inference task, estimating these parameters beta hat. Okay, and then in prediction, right, we take these parameters, these slopes that we estimated, and we multiply them by our new sort of x observations, right? And that'll give us our predicted outcomes, or y hats. Okay, so it's sort of a 2-step process. We do an estimation step to get these beta hats, these slopes, and then we use those slopes with new x's, right? And we see what are the predictions, or the predicted outcome y. Okay, does this sound sort of familiar? Maybe I see some nodding. Okay, great. So in a lot of cases, right, if the goal is just to predict what happens next, right, what exactly these beta hats are and what they mean aren't really that important. We're really just interested in like, what's the outcome, right? What's the prediction, right? But if we're trying to actually understand like an underlying mechanism, like why something is happening, that's where these betas are very important, right? For example, oh, and then, well, I'll get to that. I'll give you another example. But when I talk about inference on predicted data, I'm talking about trying to capture these beta hats when the y hat is itself a prediction, right? So here's what inference on predicted data looks like, okay? y hat here with a little underscore of AI, this means that like the outcome of our interest is itself a prediction that comes from some kind of like maybe AI black box algorithm, right? It's like some kind of predicted value that's sort of given to us. We don't really know where it comes from exactly. It's just kind of placed in our lap. And we say, okay, instead of having a true observation of the outcome, we're given some kind of prediction, but we still want to do inference. We're still interested in getting this beta hat. Okay, so this is what we mean by inference on predicted data, right? You have a predicted outcome, but you still want to perform some sort of statistical inference. And here's that same thing written sort of in English, right? So for example, in this first estimation step, we might be interested, what's the association between education and income, right? How are those two related? Does an increase in education associate with an increase in income? Maybe, yes or no, right? Depending on your data, you may or may not estimate that to be a statistically significant positive effect, right? There's a lot of literature that suggests that's the case, right? That's what we're talking about here. However, if the goal is just to predict someone's income given their education level, right? How do you make that prediction? Well, you say, I observe someone with this level of education, and in other data that I've seen, I've observed this relationship. Right, so for that person, my best guess, my best prediction of their outcome, right, is going to be informed by whatever I've seen and I've learned before, right? So we're going to predict the outcome, right? Here, right, we're saying we have sort of already an AI predicted outcome. We couldn't directly measure it. Maybe we couldn't go and ask everyone in this room, right, what their income was, but we got some kind of black box algorithm that in some way unknown to us predicted everyone in this room's income. Right? And the task is we want to, and we know what education level you have, we want to estimate this relationship between your education level and the AI algorithm's prediction of your income level, right? So that's what we mean by sort of inference on predicted data. The predicted data is the outcome of interest that comes from a prediction, and we want to do an inference task. Okay. So why does this matter? Why would we be using predicted data? This is a very nice, messy diagram of a neural network, right? This is like your ChatGPT or Claude or any of your other favorite models, right? Very complicated sort of schema of weights and edges and nodes, right? And the idea is the data that you can get, which is often cheaper and more accessible, right? This is sort of a function. It's similar to the data that you want, which is much more expensive to get-ish. Right? It's not perfect, right? But the idea is getting predictions instead of directly observing variables of interest is often a lot cheaper than going out and gathering the data yourself. Okay? So here's where the problem comes in though. Okay, I want to sort of motivate this challenge. Invalid uncertainty and a potential bias. So on the top with this gold row, right? Why true? This is like the gold standard, true observation of your sort of variable of interest. So this could be like you went to each person and you asked them their income, right? You know what it is, that's the ground truth, right? And then you also know their education level, that's this X. So when you do your regression, you get your sort of point estimate of 0.7 plus or minus some noise, right? Some uncertainty. How about we're in a setting now where instead of being able to ask everyone, maybe I don't have the resources to do a survey of the whole class, right? Instead, we use AI to predict each person's income based on who knows what, right? Whatever's on the internet, whatever your digital trace is out there, right? It doesn't matter, but the AI makes some kind of prediction, right? Maybe it's good, maybe it's bad, but it is here, it is a prediction. And we want to estimate the same parameter, right? So we're going to regress on X, which might be your income or your race or your age. And we're going to get this point estimate for each of those, right? And notice that these are not the same. The point estimates are different, so that's the bias, right? And then also this plus or minus, this error is also different. So the uncertainty around the estimate is also different, right? And this goes back to the fact that we're looking at true observed data and predicted data. And insofar as those two are not the same, right, you're going to be propagating any bias in downstream inference. Okay? Does anybody have any questions? Just threw a lot out there. Yes.
So are those are estimates, not predictions, so those are coefficients.
That's right. Thank you. Yes. These would be the beta hats and then plus or minus the standard error. Exactly. Yep. So that's our sort of uncertainty piece. Thank you. Okay, so here's intuitively sort of how you actually do this correction, right? And by correction, I mean you want to get sorry. This is sort of the truth, right? And this is what you get if you just have AI wise. And the goal is to actually recover this using a sort of statistical trick, which I'm about to talk about, right? You're in a world where you can't get all of these. You have a lot of these, right? And it's sort of like taking the best of this and combining it with this to get a correction so that your sort of ground truth and your predicted parameter are as close as possible. So this is sort of what we're looking at, okay? So this full sort of square, think of that as like the full data set, right? And then this top row is one partition. So this might be like a train test split, if you've ever heard of that in machine learning. This top row, YL in blue, this is the sort of labeled outcome of interest. This is like, we know this, we observe the truth. AI labeled, that's the sort of artificial intelligence black box model prediction, okay? And then in purple, this XL, X labeled, these are the covariates of interest. So it could be age or race or sex or whatever it might be. And so in this subset of our full data set, right, when we have all three, what we can do is we can basically learn the difference between our truth and our predictions, how they're related to our covariates of interest, right? And we learn that difference, that learned difference we call a rectifier or a correction term. And then down here, when we're in the setting where we don't have any labeled data, we don't have the ground truth data, we only have predictions and our observed covariates, we can apply that correction factor that we learned up here to the estimates that we get down there. So we're kind of pooling information when we have it up here to correct for inference when we don't have it down here. Okay, and just to write that out, step one, this sort of theta AI, this is the beta coefficient I was talking about before. I write theta because this could be a vector of covariates. It doesn't have to be just age. It could be any number of things, right? So that's going to be a function of our sort of AI predictions and our covariates of interest, right? This theta AI, that's going to be like the biased estimate. That's the estimate that you get if you don't do any statistical correction. This is propagating any bias that exists between the difference of what you predict and what you observe. And not you predict necessarily, but the prediction and the observation, right? Here, step two, this is the ground truth. So this is like you know the label of your outcome and you regress it on your observed covariates. So that's the true parameter that we want. Step three, so this is where we learn that difference. We take the ground truth, we take the prediction for the same person or the same row in our data, right? We learn that difference. By learning that difference, I mean we take the difference and we regress it on those same covariates. And this gives us what I'm calling a little delta hat, right? This is our sort of correction term, okay? And we use that, we simply add it to this term right here. This is the biased term. Adding this correction factor is going to quote unquote de-bias, if you've ever heard that term before, right? We're going to de-bias our bias estimate using this rectifier. And then we're going to be left with down here, this is our sort of corrected estimate. So that's the idea. We have information about the ground truth label and how the AI labeled that same observation. We learn that difference, and then we apply what we learned in this next step. Okay. Okay, so that's the sort of methods out of the way. And if there are questions, I can come back to it more in detail. But now I want to talk about some sort of, how does this actually manifest in the real world? How is this useful? Does anybody in the room know what a verbal autopsy is? Have you ever heard about or studied these before? I see a couple hands. Great. So verbal autopsy are actually pretty common around the world. So this is a bit outdated. This was from 2007. On the x-axis, we're showing GDP per capita. And on the y-axis, we're talking about the coverage of civil registration systems. What does that mean? This is basically the number of deaths that are recorded in the hospital system in a country. So in places where a lot of deaths occur outside of the hospital system, how do we know how and when and where those people are dying, right? The answer is we don't often know, or it's really hard to know, right? It's really expensive or difficult to figure it out. So this is basically showing you this is sort of the relationship between development and coverage of vital registration. So this is like the number of people who are dying in hospitals, right? As the country becomes more developed, more people are dying in the hospital as opposed to at home or elsewhere, right? And so a verbal autopsy is what is often used to ascertain the cause of death in settings where the death occurs outside of the hospital, okay? Instead of having a traditional autopsy, they'll actually send like an enumerator or someone to go collect an interview with the family of the deceased or the caregivers of the deceased. It will be a structured interview, usually a questionnaire. They fill out, I think I have here we go. A structured questionnaire component, right? Well, they'll say, did the deceased have over the last week symptom A, yes or no? Symptom B, yes or no, right? And they compile this basically massive spreadsheet of checking boxes based on various questions, okay? And then there's a free text narrative portion. This is sort of like a conversation that they have. So it'll be like, in your own words, please tell me about the last week leading up to this person's death. Just in your own words, right? Again, these are usually families or caregivers. These are not physicians, right? The whole point is like a physician could go and examine and do an autopsy, but in these settings, it's very difficult to get people out to remote villages or getting the person into the hospital system, right? So this is a sort of cheaper way to get at how people are dying. But as you can imagine, the sort of information you get from these interviews is not going to be as good at making predictions about how people are dying than an actual autopsy would. Another thing to point out is interviews are very burdensome on the respondents. These interviews are, I mean, first of all, right, these are people who just lost a loved one. They're bereaved, dealing with some potentially trauma around the death. And they're sat down and asked a series of very repetitive sort of robotic questions that are redundant. It's not a very good experience. And yet, like, it's kind of the best that we have. It's very important for designing policy interventions to know how and when and where people are dying. So it's sort of like the best that we can do, but it's very burdensome. And this is sort of what the pipeline looks like. The way that we actually sort of form consensus scientifically and also roll out sort of different interventions and different public health policies. So on the top left, right, a death occurs and is reported. Someone comes and conducts an interview. This is that verbal autopsy interview, the structured questionnaire and the text narrative. These data are uploaded to a database. Data quality checks happen, right? You get rid of stuff where people maybe didn't answer properly or there's something wrong with the data. There's pre-processing, and then this is the piece where the prediction actually happens. So when I say prediction, the goal is to figure out, we have a person who's died, how did they die? That's the prediction task. And you can imagine a simple way you could do this is you could take that sort of spreadsheet that you filled out with the checkboxes and you hand it to a physician and you say, based on these symptoms, what is the most likely cause of death? And they would use their expertise to try to give you an answer. Right? That'd be like a very simple prediction algorithm, and that's one way people do this. All the way up to a super complicated neural network, ChatGPT or whatever it might be, and everything in between, right? So there's some kind of prediction task going on where we're predicting the cause of death based on the information gathered in this interview. And then finally, given those predictions, then reports, papers, articles, and decisions are made. That's sort of the regression task that I was talking about, right? We have an aging distribution, right? What is the association between an increase in age and the probability of dying from maternal mortality compared to cancer, right? That's the kind of question we're getting at here, right? In this population at this time, what does the distribution of causes of death look like? How is it changing over time? How does it change with changing population demographics, interventions of different drugs or pandemics, right? All these things. That's the sort of prediction cause of death into inference task, right? Okay. So in this work I'm talking about today, we had two main questions. The first question was, what if we rely only on the text narrative portion of the verbal autopsy, right? We completely ignore the sort of structured text or the structured questionnaire data and just look at the text. And then the second question is, does doing this inference on predicted data correction that I started the talk with, that statistical correction, does it change our conclusions, right? And when I say change our conclusions, I'm specifically talking about if we estimated in the sort of biased case where we're just using predictions, if we found that various variables are statistically significantly associated with the outcome or not, right? Do those associations change, right? Does a positive effect become negative? Does a significant effect become not significant, or vice versa, right? These are the kind of questions that we're trying to get at with our conclusions, right? Because at the end of the day, if you're a policymaker, right, you're interested in variables that are statistically associated, right? P-values is another way that people talk about these sort of scientific conclusions, right? P-values are one way that people make decisions, right? So does the P-value change over that threshold of 0.05 or not, right? That's kind of what we're getting at. Our data come from our good friends just down the road at IHME. They gathered these data over a number of years, starting in 2005. And so these data are collected in 6 sites in 4 countries. And the really, really nice thing about this data set is for every single observation, there's nearly 7,000 observations of adult deaths in this data set. For every single one, there was a verbal autopsy and a traditional autopsy, right? And the reason that this is so helpful is because, as I mentioned earlier, verbal autopsies are most common in places where traditional autopsies are not accessible. So it's really uncommon to have both a traditional and a verbal autopsy for the same patient, right? In this case, we do. This was collected specifically for scientific inquiry, right? And the reason that this is really helpful, right? We have a validation set, right? We know the quote unquote ground truth because we had a traditional autopsy, right? A physician actually performed an autopsy on the person, right? As well as the verbal autopsy. So this validation set allows us to evaluate how well we're doing, both with predictions and with inference. Okay. Okay, so our leave one out prediction. So this is sort of the experiment that we're setting up. There are 6 plots shown here. Each plot is one of the different sites where data were collected in 4 countries. And because we know the ground truth, the true autopsy report for each patient in each of these 6 sites, what we did is we said, okay, we're gonna take 5 sites and we're gonna train our model with those data from those 5 sites. And then we're gonna predict in the 6th site that was left out, where none of the observations from this site were seen in training, right? So we're kind of pretending like we don't know anything about this one site, training a model elsewhere, and then seeing how well it performs in context, right? That's what we mean by leave one out. And we do this same experiment 6 times with each site being the one that was left out, if that makes sense, okay? These bars, this is just the distribution of causes of death, right? So there are 5 different causes of death, broad categories. And you can see the top bar in all 6 sites is non-communicable disease. So these are like your cancers and your heart diseases, okay? Non-communicable disease. But then after that, right, there's a lot of heterogeneity, a lot of differences in how people are dying in these different sites. You look at a site like this is Mexico City, Mexico, very, very few maternal mortality. This is deaths due to childbearing or childbirth, right? Whereas in Pemba, right, in Tanzania, there's a lot of maternal mortality, like relative to the other causes of death, right? The total numbers are quite different. This is only 260 observations compared to 1,300. But within the total distribution, you can see maternal is a much, much higher cause, right? So there's a lot of variability in these sites. So as you can imagine, right, if you're training a model on data that looks like this, and then you're trying to predict in a place that looks very different, you might expect to see some bias in your predictions, right? It's going to get some things wrong. It might over-predict, right, these categories here that are relatively uncommon because it's looking at data where it's actually relatively common, right? So that's the sort of experiment. We tried a bunch of different models. This is the prompt that I used for the large language model. Has anyone in here worked with an LLM before? ChatGPT or any of those types of models? Yeah. So this is like what I typed in basically, right, to get the answer, right? So in here, in this little narrative section, I'm going to give it each narrative. This is like each verbal autopsy narrative. And then the prompt looks like this. I give it a very short amount of context about what each sort of cause is sort of containing. This is not an exhaustive list. It's just to kind of give it some context. Here, I tell it, okay, these are the only outputs I want. I want you to pick one of these from this list and only one of these. right? And then my actual instructions are just down here, right? So this is called prompt engineering, right? It took a lot of iterations and a lot of trial and error to figure out exactly how to set all of this up to give it to the chatbot and get it to give me the responses that I wanted. Okay, and I'm happy to talk more about this later. But what does it look like? Okay, so here's the prediction accuracy of all these different models. So on the left, or sorry, on the x-axis here, naive Bayes, support vector machine, k-nearest neighbor, and BERT. These are all different NLP, natural language processing models used to make predictions. Okay, and you can think of these as sort of like older, kind of maybe less flashy, less sexy models compared to something like GPT-4, right? This is kind of like state of the art like 20 years ago, right? But as you can see, like the prediction accuracy on the y-axis, right? 6.64 means it's getting it right 64% of the time. These sort of older, outdated models are actually performing really, really well compared to GPT. And we were really surprised at these results because we thought GPT, even though the prompting took a long time, we thought GPT would do much better. So this was kind of a puzzle. So we looked a little bit closer at the predictions GPT was giving us. In this narrative column, this is the text narrative that we gave it, right? And this is the full text narrative for that patient. So for example, in the first column, respondent thanked for being visited. That was the only information we had in the text narrative to make a prediction about how someone died. We knew the true cause was AIDS tuberculosis, right? We knew that because of the traditional autopsy that was performed. The prediction from GPT says the narrative does not provide enough information to determine a cause of death, which is actually great because it shouldn't be able to make a prediction based on what we're giving it here, right? So in many of these cases, right, no comment. The client asked for the service, right? Most narratives were not like this. This was a small amount, well, 1,500 out of almost 7,000. So not a small amount, but most narratives had information, but some of them didn't. And the nice thing about using GPT was it actually told us when it didn't think the narrative was useful, right? So if we drop these observations from our analysis, now the accuracy of GPT is much better, right? It's doing a much better job at predicting cause of death from the text narratives when the text narratives do contain actual useful information. Okay, so far this has all been about predictions, okay? This is another sort of graphic going back to the inference on predicted data. So now when we want to do inference using these predictions, this is how it looks. We start with our verbal autopsy text narrative, right? It goes into a prediction. We get a predicted cause of death. And then we know the true cause of death from that same observation because they have a validation set. So combining these two, right, we get this sort of correction factor. This is like telling us when the prediction disagrees with the ground truth, right? Write it down, keep track of where these are happening and how they relate to the covariates of interest, like age, right? Keep track of that. And then over here, when we're in our unlabeled data set and we get our prediction, we don't have the ground truth, right? This is our sort of leave one out experiment. We're going to use this correction factor that we learned when we did have it to make the correction of the parameter of interest. Okay, so this is that sort of prediction pipeline into an estimate. I'm going to go ahead and skip over the loss function. This is if you've ever worked with a machine learning model, right? The loss function is just kind of the thing that you're trying to optimize over to find those betas, right? So I just wanted to put it in here in case anyone, I'm going to share the slides later if anyone wants to look more closely at the paper or at this. This is the loss function that we're using. And the main thing to look at here, this lambda in this full expression is a tuning parameter, which just means that it takes on a value from 0 to 1. It takes on a value of 0 when the sort of predictions are useless. They're really, really noisy and not helping, right? And it takes on a value of 1 when all of the predicted data are super useful and they give you a really good signal, right? So this tuning parameter is basically another thing that you estimate with your data. And it's really nice because it kind of tells you something about, hey, based on our modeling, these predictions are actually really useful or really not useful, right? It's nice to know. Okay, so now to the scientific question. How does age vary with cause of death, right? Is an aging population associated with an increase in this type of cause of death? versus relative to another, that's the kind of question of interest, right? Some more math. Feel free to not look too closely. I just wanted to point out that what I'm going to be showing you results of is a multinomial logistic regression, which just means that the outcome of interest is going to be cause of death categories, right? So those bar charts that I showed you with the 5 causes of death, right? The outcome of interest is 5 unordered categories. So that's why I'm using this type of regression. And the thetas, right? The point estimates I'm about to show you, these are the slopes on age, right? So this is going to show you, right? I'll just read one of these out. For every 1 unit increase in age, the odds of dying due to a communicable disease compared to dying from AIDS tuberculosis are expected to increase by that slope. Okay, so again, just a little bit of math for the math people in the room. I will translate it all into English. These are what some of the results look like. So I'm plotting in Uttar Pradesh in India, that's the site, and NB, that's the model, naive Bayes was the prediction model, okay? On the Y or X axis down here, these are our cause of death categories. Notice there's only 4 of them and we have 5 causes of death. That's because the 5th cause is a sort of reference category. In a multinomial regression, you have 1 category that's left out as the reference. So in this case, AIDS tuberculosis is the reference category. And on the y-axis, this is the change in log odds, right? So kind of how likely something is, okay? And the way to interpret this is ground truth is in yellow. So this point estimate is saying that the log odds of dying due to a communicable disease compared to dying from AIDS tuberculosis increases by this much with a 1-year increase in age. So as you get older, you're more likely to die from a communicable disease than AIDS, right? That's what this numerical relationship is describing. This is that coefficient. And then you've got the error bars. This is the 95% confidence interval. And the thing to point out is for each of these, you can think of this, this yellow as the ground truth. This is the inference that's done with full access to all of the good labels, okay? This blue, this is the naive estimate. This is the estimate that's using only the predictions. It doesn't see any ground truth. One thing to point out is the point estimates are biased, which means that the sort of points are, in this case, they're all biased upwards. They're all higher than the ground truth. And if you look at the uncertainty intervals, the uncertainty intervals are much, much bigger, okay? In purple, this is what happens after you perform the sort of statistical correction that I was talking about, right? And you can see that while they're not exactly the same as the ground truth, they're a lot closer than the naive estimate, right? And the uncertainty is actually a little bit smaller, which is great, okay? So this is one site and one model, and we did this experiment many, many times, right? We did the same experiment for each of the sites being the one left out site. Each of them had 5 different models. So if you want to do some quick math, we have about 100 of these plots, right? So I'm just going to show a couple to highlight kind of what's going on. So now we're in Mexico City, and we're using BERT as the model. And the question is, do our conclusions change? What do we mean by that? Okay, so let's look at external cause of death. We have ground truth here, and I had this little red line going across at 0. So remember how I talked about p-values earlier? P-values are how we sort of assess statistical significance. Is this variable associated with the outcome statistically significant, right? Well, with a sort of cutoff of 0.05, right? That's our sort of alpha in our significance level. That kind of determines how wide the confidence interval is. And if the confidence interval overlaps with 0, right? Like it does in this case, or it does in this case, or it does in this case, that means that these estimates are not statistically significant, okay? The uncertainty interval includes 0, which is another way of saying we can't rule out the fact that there's no effect, right? That there's no association at a 95% confident level. So in the case of communicable disease, with this specification here, all 3 estimates are statistically significant. None of them overlap with this sort of red line. Okay, so we wouldn't necessarily change our conclusion here. But with external, right, the ground truth says this is not statistically significant, right? Age is not statistically associated with increased odds of dying to an external cause. This would be like a road traffic accident or homicide, okay? If we were just using our naive predictions from ChatGPT, right, we would find, wow, not only do we have a big effect, it's also statistically significant, right? This is an effect that a policymaker would look at and potentially design policy around. We need to do something about external causes of death because they're associated with an aging population, right? It turns out when you do the statistical correction, you're back down here, no longer statistically significant. Okay, so this piece right here is an example of what happens when you're doing sort of biased inference, right? You're performing invalid statistical inference. You're going to draw conclusions that you might not otherwise draw if you had a better data source. Okay, so I'm going to skip over. I have a couple more plots that show sort of similar things. But now I want to switch gears really quick. Okay, and I want to talk about another project that I'm working on that's some ongoing work. And it's on the body mass index. Okay, so I'm going to try to sell you on this because part of this requires sort of an intuition leap. Okay, so bear with me and let me know if this is compelling or not. So the outcome of interest that we're talking about is obesity, right? What is obesity? Despite obesity's designation as a disease, in fact, as an epidemic, right? It lacks a biologically specific definition. And by that, we just mean that what it means to be obese means you are somehow too heavy or you have too much weight to the point that it becomes unhealthy, right? But exactly what that looks like and how it manifests is super unclear biologically, okay? So just the concept of obesity itself is very squishy, what do you say, right? It's not very rigidly defined. And the other tricky part is there's a lot of ways to measure obesity, right? So you could use something like measuring someone's body composition, right? Using a DEXA scan where you could say, this is the total percentage of your subcutaneous fat and visceral fat and bone density and muscle density, right? This is a very, very specific measure, but it requires very expensive machinery and a whole process to measure this, right? The body mass index, right? This is the ratio of someone's height to weight. Okay, this is another way to measure body composition and is used to measure obesity. There's other things like the waist circumference ratio. There's also like water displacement. There's those like really fun calipers that people will use in front of your classmates, like the worst thing, right? So there's a lot of ways to measure this. And the point that we're trying to get at, the sort of argument that we're making is that the body mass index, you can think of it like a prediction algorithm. It's not a fancy or complicated prediction algorithm, but what it's doing is it's mapping someone's height to weight or height and weight to a health category. And if you just think about that for a moment, right, like height to weight to a health category, right? You are or are not healthy from height to weight. This is a prediction, right? And it relies on looking at some kind of sort of quote unquote training data, right? The BMI score itself is a continuous variable, right? It's a ratio, but then the ratio is put into these different bins. So you've got normal weight, overweight, obese, right? With these different bins, okay? And so the question is, how predictive is BMI? 47% of patients had a fat percentage that did not correspond to their BMI classification in this recent study. Okay. So are we convinced or not that BMI is a good measure? Well, because BMI is so cheap and easy to collect, it's often used regardless of how quote unquote good it is as a measure. It's really convenient, right? And there is a correlation. So what here I'm showing you, this is data from N. Haynes, the National Health and Nutrition Examination Survey in 2017. In this like peach color, I have the BMI for all of the people in this data set. In the dark blue, this is the distribution of DEXA scanned total body fat percentage. And as you can see, there's a lot of overlap. That's this sort of middle distribution, right? But it's not a perfect overlap. So this is just a quick eyeball test to show that while these two things are related to one another, they're by no means the same. They're certainly not the same, okay? So here is an IPD correction. So actually, before I show this, the intuition, that the thing we're trying to sell, right, is in inference on predicted data. The setup goes, you have cheap predictions that are easy to collect, like the BMI, right? And then you have an arguably better measure, like total body fat percentage. This is arguably, and this is not a secret, right? In the literature, this is known to be a better predictor of health outcomes, right? Your actual like body fat percentage is far more predictive of health outcomes than your height to weight ratio, right? So we're in a world where we have access to BMI, but we wish we could do inference with a better measure like the DEXA scan body fat percentage. How could we correct our inference to look more like we're working with body fat, right? To better capture like people's actual experience, right? We can use IPD, inference on predicted data. So this is the setup. On the x-axis, this is an odds ratio. So an odds ratio of 1, this sort of vertical dotted line, basically means that there's no change in the odds that you would be classified as obese with a change in whatever your category is on the x-axis or the y-axis, okay? And on the y-axis, we're looking at ages. We're looking at how active someone is at work, how active someone is in leisure time when you're not at work, how much sleep you get, and smoking status, okay? So this is just a regression that comes from a different paper and they use different data. But the goal of the paper was to say, what is the association between sleep, how much sleep you get, and how much smoking you do? Are you a smoker or not? What are the effect of those things on the likelihood of being obese? Right? Are these things related? And in red on top, this is the sort of estimated coefficient that you would get if you just used BMI as your measure for obesity. Right? If your obesity or if your BMI was more than 30, you were classified as obese. That's this red line. The blue line is the correction. So this is sort of that counterfactual that says in a world where you had access to sort of the better measure of body fat percentage, right? If you do a correction to look more like that, that's what you get in blue here. And in purple, I've highlighted all of the cases where just using BMI, your conclusion would be that it is statistically associated with an increased likelihood of being obese. But then when you do the correction, it's now overlapping with this, this 1. It's no longer statistically significant. So just like take a moment to like, I mean, for me, when I first ran these numbers, I kind of had to take a step back and be like, did I do something wrong? Because like finding that smoking is not associated with being a more obese goes against a lot of what is currently published in the literature, right? And a lot of that is due to the fact that they're using BMI to operationalize this variable of obesity, right? When you use a sort of quote unquote better measure, no longer associated with smoking, right? So just as a qualifier, this was just one experiment with one set of data and one regression specification here, right? So this is ongoing preliminary. These are preliminary results from ongoing work. There's a lot more to do here, but just to give you kind of a sense of what the implications are of using this kind of correction, this is another place that I think there's a lot of great opportunities for future work. So really quickly, some limitations from both of these. In the verbal autopsy setting, multilingual translations are not lossless. Okay, by this I mean that in country where people were dying, the interviews were conducted in the local native languages. Those interviews were then translated into English by humans in those countries. And then those translations were then put into an English language model. Okay, and at each step of this process, going from what was spoken by the interviewee to the output of the prediction model, before it even gets to the prediction task, there's translation going on from native language into English. And this is not lossless. So we don't have a Tanzanian language model, right? We likely will never have one that's as good as GPT. That's just the truth. So this is a limitation, right? We have to think about information loss when we go from Tanzanian into English and then use that in a language model. So that's one limitation. We're looking at 5 cause of death categories. Of course, these are aggregate, right? So like non-communicable contains many, many diseases. It's a lot harder, but it would be much more helpful scientifically and policy-wise if we could make this more into more categories, like a 35, 40 cause of death category list, okay? The ground truth, I say gold standard of ground truth, but in reality, even with a traditional autopsy, two different physicians could disagree about a cause of death given the same observation. So there's by no means consensus in the medical community, even when it comes to a traditional autopsy. But we point those out because we really think about ground truth as like the best measure you can get, right? Which is often the more expensive one. For the BMI study, first of all, healthy weight as a concept is itself contested, right? At a population level, there are associations between negative health outcomes and being overweight. But at an individual level, this is a very, very basically spurious association. There's not a lot of great science or great evidence right now, conclusive evidence. So this is a very contested concept. And then same thing with the BMI and obesity. There's no ground truth measure of obesity, right? Partly because as a concept, it's just not biologically defined very well. So it's very hard to think about what even a ground truth means when we're thinking about obesity. So conclusions to take away, this is a procedure that you can use anytime you're working with predictions and you want to do inference. Text narratives can be really useful in place of these structured questionnaires. So as I mentioned earlier, these structured questionnaires are like super repetitive, very redundant, a big cognitive burden on the families that are bereaved and mourning. And so if we can move into in a practical setting, if we can move into a world where these interviews are instead like a 15-minute phone interview, and we can get everything that we need from that and still do really good, high quality science, that would be a much, much better system, both for the science, but also for the people who are actually like living in these situations. And then when we do this sort of correction on all of these different medical experiments that are interested in BMI as an outcome, we may or may not draw the same conclusions as if we used the BMI. Okay, so thank you all for your attention. I appreciate the nods that I've been getting. It's very encouraging. My name's Adam again. Here's some information if you would like to follow up on this work. You can see the full paper, some of my other projects on my website. And if you are doing any research yourself and you like to code in R, great news for you. We have software available that is ready to use out of the box if you want to do any of this yourself. I wanted to make sure I left some time for questions and comments and concerns. So yeah, I'll open the floor to anyone who has comments or questions, and also anyone on Zoom who would like to chime in, feel free.
All right, thank you.
Yeah, thank you. Yeah. I'm going to go back a bunch of slides. So here's the sort of like big picture of how you learn this correction factor. You take the difference between the prediction and the observed. So like this blue, this is like the observed label, like cause of death was AIDS. And then this is the difference. Maybe it agrees and it also said it was AIDS, right? The AI prediction, in which case the distance is 0, right? And you learn how that is associated with age, right? And then the next observation, you do the same thing. You see the difference, right? And in the computer, right, these variables are coded as numbers. So there is like a numerical difference, right? Even though like for us, like the distance between maternal mortality and AIDS tuberculosis, like there's no, right? But in computer embedding space, there is a numerical difference. So you learn that difference and you regress it on the X. Yeah. Yeah.
So what was the reason on choosing Mexico City as the testing data?
That's a great question. So let me go back here. So we have Mexico City, Mexico, Andhra Pradesh and Uttar Pradesh, both in India, Dar es Salaam and Pemba in Tanzania, and then Bohol in the Philippines. So all of these were sites that were collected in the original, this data set. These are places where IHME have like partners in country and they have relationships and they go and they perform these autopsies and verbal autopsies. For our experiment, so we did predictions in Mexico City, but then we also did a prediction with Andhra Pradesh where this was the left out site and we trained on the other 5. And then also for Uttar Pradesh. So we did a a prediction in each of the 6 sites using the other 5 to train the model. We trained 6 different models, and then we compiled all the results into what I showed at the end. Yeah, so we used all of them, and if we had more data, then we would have used that too. We were only looking at adult deaths. There's in this data set, there's also child mortality and even neonatal. So this is like age less than 1, age 1 to 5, and then or 1 to 14, and then 14 plus, I think, for adults. So we were even looking at a subset. And part of that is because the cause of death distribution looks very different for neonatals, for children, and then for adults. So we were just looking for one part. So that's another limitation.
Yeah.
But
thank you.
yeah, thanks. Good question. Anybody else? I saw one maybe over here. Yeah.
If you were deciding whether you want to have the option with a small subset of ground truth data versus using your model, is there a threshold for the accuracy of your model that you need to reach to be able to use that over?
Yeah, that's a really good question. So to just repeat on Zoom in case you couldn't hear, how would you sort of decide when you're choosing your model how much ground truth data or prediction data to use? And is that more or less your question? Great. And then the follow-up to clarify is what prediction accuracy do you need those predictions to be to actually use them to make good interventions in policy? It's a really important question, and the answer is it kind of is complicated and it depends. The short answer is if the predictions are really bad, like low accuracy, then the way that we have specified the model is it's basically not going to like use those data. It's going to rely only on the very small subset of like actually gold standard labeled data you have. If, on the other hand, so like, for example, when you go back to these cases where, right, like these were like useless, right? And so in the case where like we weren't using GPT and we were using an older model, what it would do is it would say, this doesn't seem very useful. I don't know what to make of that. I'm going to make a prediction that you died of the most common cause of death in what I'm seeing, because that's the most likely to be right, right? So it's making all of these predictions that, in this case, it would be communicable death, or communicable disease rather, when that's not necessarily the case, but that's its most likely outcome when it doesn't have any signal. And so to answer your specific question, if the predictions are bad, the accuracy is bad, you can see the difference between the naive estimate and the ground truth is like pretty big here. This is a setting where we're using naive Bayes, which is one of the worst predictive models. If I go down to GPT-4, which after we discount for the sort of useless narratives, you can see that while there's differences, the differences are a lot smaller, right? The difference between the ground truth and the naive estimate, and then the correction after that, they're all pretty close. And that's because the predictive accuracy is actually really good. And so when it comes to making policy, we're sort of in a world where we're in this like purple, and we don't actually get to see yellow. We don't know the ground truth. The really nice thing is even in settings where the predictions are very good, which means the estimates from our naive are pretty close, right? Look at the purple and how it relates to the yellow. And then go to a case where they're farther apart, right? This one, the prediction accuracy is really bad, but the purple is still close to the yellow. So the really nice thing is even if the predictions are not good, this gets pretty good estimates. And one of the really nice implications that I didn't really talk about is when we look at the models that we used. Oops, wrong way. Here we go. So naive Bayes, SVM, KNN, BERT. So these are like basically free to use. They're like super cheap computationally. They're very easy to run. You could spend an afternoon and like do what I did, and it'd be very fast and cheap. GPT, I mentioned at the beginning, the computing credits from eScience cost us about $3,000 to do this analysis. Really, really expensive working with like all these tokens, all this text data. And like, while we got better accuracy, it's not really that much better, right? And so one of the implications is like, we don't actually need like a super fancy bells and whistles model to make these predictions. right? It might get it better on average a little bit, but when it comes to doing the inference isn't any better, right? The inference is the same. So thank you for your question.
Right, thank you so much, Adam.
Thank you.
Is the BMI going away? Because it's been a lot of like hammering.
Yeah, that's a good question. I don't know. Yeah, how do people feel about the BMI pitch? Do you buy my claim that we can think of it as a predictive algorithm, or does that seem crazy? I see one thumbs up. I don't know.
I just bought a scale that has the BMI.
Oh, it does. Okay, wow, yeah.
I'm not gonna look at it.
Yeah, exactly. Right. So there you go though, right? Yeah, awesome. All right. Well, thank you all so much.
Thank you.
Yeah.
Thanks.